Okay, you can see that, I presume. Okay, so my name is Iain Guilliard. I'm from the Australian National University in Canberra, Australia, and I also work at NICTA, or Data 6.1 as it's now called, in the Canberra lab as well. So my presentation today is on some recent results and using mixed integer linear programming to solve traffic optimization problems. So our motivation here is to maximize utilization of the existing infrastructure. We want to reduce congestion, optimization of signal control. So we'll just go through the different methods of signal control just to introduce the topic. So we have this first category, which I call suboptimal, where we use things like fixed time control, the most basic form of control, where we have fixed schedules loaded into the controller, and they're executed regardless of the state of the traffic. They're probably based on some sort of survey data, but they're not necessarily optimal, at least for the particular traffic on the day at the time. And then more advanced forms of control from there include effectuated control, where perhaps we have some sort of loop sensor in the road and we can skip phases if there's no traffic waiting in a side street. And then we have more advanced forms of control such as scoot and scats, where we adapt the control plan, again sensing traffic in the network and adapting the control plan to try and optimize that for the volume of traffic in the network. So these have the advantage of being easily deployed, decentralized and reliable, and cheaper as a result. But we have no performance guarantee, whether they have no means of adapting to the traffic level or being heuristically based rather than optimal. Which sort of leads to the next category, which I call locally optimal. And we have some emergence of these in recent years, where there's some attempt at trying to optimize the signal plan, at least locally, for an intersection. So typically we can measure the traffic in more detail, perhaps using cameras and computer vision to try and get a more exact location for the traffic along a link and the speed at which it's traveling. And from there try to optimize the signal plan, perhaps using some sort of planning, optimal planning algorithm. So again, typically they're only based on local control, so they're decentralized and reliable and easy to deploy. But because they don't coordinate across the network, they're myopic. So again, they're not necessarily globally optimal. They're only locally optimal around one intersection or a small set of intersections. So the goal really is to have globally optimal control across the entire urban network, where we can coordinate intersections to achieve an optimal level of signal control, and that would represent the best we could possibly achieve. But we need to scale our control algorithms up to achieve that, which is the main problem to solve. So in this work, I'll present a new model of traffic signal control based on mixed integer linear programming. So we leverage off the massive improvements in the performance of linear solvers in recent years, and we define a new model that supports globally optimal signal control. So our model supports arbitrary topologies. We can have grids or any shape you like at the intersections. We can have arbitrary traffic light phases to support complex phase architectures around an intersection. And it captures the important traffic dynamics that we need to generate optimal plans. So it captures platooning and queuing effects quite well. And it's a very simple model. It only has 3 continuous variables and 1 binary variable per link. And typically the cost of a MILP or mixed integer linear program is a function of the number of binary variables. So get it down to just one per link, and that helps with the scalability. And perhaps most crucially of all, it's a non-homogeneous model. So we can have arbitrary sized time steps, and we'll just look at in a little more detail about what that actually means. In terms of the time discretization, we can either have a homogeneous time discretization where the discretization is evenly spaced. Each time sample is the same distance apart, or we can have a non-homogeneous, so we can have some uneven spacing between time samples. And so one way to exploit that is to do a fidelity trade-off. So we can, for the same number of samples and therefore approximately the same costs, we can solve over a longer temporal horizon. So we can have a longer plan, same number of time samples or same number of binary variables. And this has the effect of also increasing the spatial horizon. So since the distance between intersections is a function of the travel time of traffic in the network, if we can increase the temporal horizon of the planner, then we can also see the effects of choosing a schedule for one part of the network. We can see the influence of that on another part of the network over time. So we would hope then see more coordinated policies with that. So I think you can see that there where the horizon of the increase in the temporal horizon also increases the spatial horizon of the network. So I'll show you an example. So we understand what we're looking at here. So this is a street view overlaid with a QTM model. So it's a link and node model. So we have a link along each street or each segment of the street between intersections, and each node represents an intersection which can be either controlled by signals or not as needed. And so if we take this model and we flow some traffic through the network, this is what you see. So here we just have a fixed schedule. We haven't tried to optimize the signal plan. It's endogenously fixed. And what you're looking at here is in green is the prediction of traffic flow at a macro level by the QTM, by the Q transmission model, and overlaid onto that the black dots are a micro simulation of the same signal plan. So you can see there's a pretty good correlation between the micro simulation and the QTM prediction of traffic flow, and the intensity of the green represents the density of traffic. So you'll notice as the black dots are tighter together, we have a more intense. So that's also being captured by the model. And we can see this model captures some important dynamics. So you can see the queuing behavior there along this avenue when the lights turn red, the queue builds up and then dequeues when it turns green. We capture platooning effects. So you can see traveling along this link, you can see platoons of vehicles. And this is important because we can then, the planner can then choose a policy that will try to coordinate the changes of the lights from red to green to line up with the arrival of platoons. And hopefully we will get effects such as green waves or green corridors along arterial routes, which is something that Convergence can be used to try and improve traffic flow. And the model also supports term probabilities, so we can have traffic leaving a link can turn into side streets or travel straight ahead. So you can see that intersection, for example. Okay, so let's look at the model in a bit more detail. So just looking at a simple single intersection with 4 links, 1 coming in and 3 going out. So each link consists of a set of exogenous variables and internal variables. So we have propagation time for the link, which is the time it takes traffic to flow from one end of the link to the other at free flow speed. And we have inflows and outflows into and out of each link. So the flow can either be external, so it can be coming from outside the network or leaving the network, or it can be internal flows from one queue to another. So we can see that here we have a flow coming into Q1, we have some internal flows out to queues 2, 3, and 4. Depending on the term probabilities, the flow will split across those outgoing links, and then it leaves the network from those links. And associated with Q1 is also a traffic light, which will modulate the flow out of that link. So we use a vertical stacked queue at the stop line. So all traffic entering the link will flow down the link at free flow speed. Then on reaching the end of the link, we'll enter into a vertically stacked queue. If the light's green and there's no queue, then it'll just travel straight out. But if the queue has built up because the light's red or there's downstream congestion, then it will build up in a FIFO queue. And as soon as the congestion frees or the light goes green, it will dequeue and flow out, as you saw in the previous example. So even though that's kind of a simplified way of machine queuing behavior, we can sort of think of this vertically stacked queue as actually progressing back down the link. But even though the traffic will always flow right to the end of the link and then enter into the queue, actually once a queue is formed, we don't really care about that. The queue dynamics are now dominated. The link dynamics are now dominated by the queue. So you can think of it as just being a horizontal queue where it's effectively dividing the link up into a congested region and a free flow region. So, so while that's a simplification compared to some other macro traffic models, it's capturing really the important characteristics for urban traffic networks. And, we can have a look at that in a bit more detail. So, so here, just looking at a link, we've got some cars that are in free flow in a platoon traveling down the link, and we have a queue that's built up at one end. And below that, try to represent the way QTM captures this. So we, because we have piecewise linear dynamics, we can capture the exact locations of this platoon at a given time, and the size of the queue at a given time. So if we contrast that with some other macro models, such as the cell transmission model, CTM, we can only capture the density within each cell. So we have to divide the link up into cells, and we can only capture that, approximate that as a function of the number of cells that we have. So we have to have an increasingly large number of cells to try and accurately capture that platooning or queuing effect. So while CTM has been very good for capturing traffic dynamics, something like a motorway or freeway where we have long links, and we tried to capture that the full fundamental diagram of traffic flow with congestion and free flow. For dense urban networks, we're not really so interested in that. We just want to, once we have queues forming up, but the network is dominated by those queues, and not really so interested in the dynamics along the link. So looking at it in a slightly different view, so here's some graphs showing the evolution of some of the queue variables in a network. So here we can see how it's piecewise linear. And we only need to sample wherever there's a piecewise linear change in the state of a variable. So, so here you can see the light is red at L6, so a queue is building up at Q1, and then sometime later it changes to green and the queue flows out. So we need a time sample at this point to capture that piecewise linear change. And at the same time, L7 goes red and a queue starts to build up behind L7, and then eventually, we get the queue building up and spilling all the way back to the next intersection and reaching saturation. So we need to have another time sample capture that piecewise linear change. So we can. So in principle, we only need to sample at these points. Of course, actually finding these points is perhaps more problematic, and I'll come back to that later in the presentation. But one approach is to just discretize some chosen discretization, and as we increase that discretization, we'll converge on the actual real solution. So here we see increasing discretization, and we see how it converges. As we increase the discretization, it converges on the true solution. So we can exploit that for our non-homogeneous discretization by, as we saw earlier, we can focus discretization more densely at the beginning of the plan, where we want high fidelity, where we're going to execute this plan on the network quite soon. Whereas for the rest of the plan, we're just going to throw it away. We're not going to execute that on the network necessarily before we replan and update. So we just want to approximate the traffic flow, and we can see how that converges depending on the level of discretization. And one of the other problems we need to solve, we need to find at each update step, each time sample, we need to update the state of the variables, and to do this, we need to find the volume of traffic that's arriving at the input to the queue. So to do that, so for a given time interval, we have delta Tn, we need to find the amount of traffic that was arriving at the propagation time ago, at the when it first started flowing into the link, to arrive at that time later. We need to go back in time and look at that point, and of course, depending on the propagation time and the discretization we've chosen, it may not line up with the discretization at that point in time, especially if we've used a non-homogeneous discretization. So we need to have some way of dealing with that. So what we're looking at here is a time distance plot. So we're looking at we have time along the horizontal axis and distance along the vertical axis, and we're seeing how the flow moves through the network along each link. And so here we have 3 links separated by 2 intersections, and the horizontal bars represent the traffic light turning from red to green. So the solid bar is red, and the lighter color is where it's green. So looking at that in terms of the Q input variable, so here we have the discretization and the corresponding evolution of that variable over time, and we're trying to find the volume of traffic that arrives during interval n, highlighted here in red. So to do that, we go back the prop time ago, the time at which that traffic would have arrived at the beginning of the link. And we look at the intervals that are covered by delta t at that point in time. And as you can see here, this could cover across several intervals at that point, or even parts of an interval. So we need to find each of these intervals, or parts of these intervals. We need to find the volume of traffic, add them up to find the total volume of traffic that's arriving. And because the model is piecewise linear, we can exploit the fact that the flow is constant over an interval. So actually, we can just integrate by dividing the Q input by the time interval to find the rate of flow, and then integrating by multiplying by the time for the partial. For the partial interval, we can just multiply by the time covered by that interval, and so we can then sum across all of those intervals to get the total flow arriving using this equation. So here are some of the constraints that we use in the linear model. So you can see here the update step. We use that integration function that I just showed you previously to find the traffic arriving. So for each interval, we take the previous state of the queue, we subtract all the traffic that left during the previous interval, we add all the traffic that arrived during that interval, and then we have the new state of the queue. And we have some other constraints that we apply. So we try to ensure that the total traffic in the link at any one time doesn't exceed the capacity. So that the sum of the traffic that's waiting in the queue and the volume of traffic that's traveling down the link has to be less than the capacity. The number of cars that can fit on the link at the jam density. When the traffic's all stationary along the length of the link. And we introduce term probabilities, as we saw earlier, so we ensure that each flow is only the proportion of the term probability of the total flow out from the link. And we integrate over all of the flows leaving and entering the link to get the total volume coming in and out. And finally, we modulate flow leaving the link by the binary variable that represents the state of the signal, red or green. And additionally, we have constraints to control the phase duration. So we want to have some control over how long we have green and red lights for. So we have a minimum phase time and maximum phase time for each phase. We have maximum and minimum cycle times. And to do that, we have a duration variable associated with each phase. And we trigger constraints off the state of the phase variable itself to do that. So we have constraints that we activate when the phase is active to accumulate the duration of the phase. So here in this ramp phase, and then when the light turns to red, we trigger. We turn off those constraints and we turn on some constraints to hold the variable state, so that we can use it later to apply the minimum maximum constraints. And just at the point where we change from red back to green, we reset this duration back to 0. And so then, whenever the light is red, we can apply, we have the duration of the previous phase execution time, so we can apply minimum maximum phase constraints to that. And also at the end of each cycle of all the phases in the traffic light, we can sum across all of those phase durations and apply some minimum maximum by triggering off the very last phase in the cycle. We can apply the maximum cycle times as well. We also need an objective function. Here we've chosen to try to minimize delay in the network. So we try to minimize the total travel time for all the vehicles in the network. And to do this, we maximize flow in the network. And show how that corresponds to delay. So what we do here, we wait in the objective function for the linear program. We wait the flows in and out of the network by the time remaining in the plan. And so this encourages the solver to flow traffic as much as possible, as early as possible. So here we're looking at arrival departure, cumulative arrival departure curves for the network. So the green is the upflow from the network and the blue is the inflow. And this objective function has the effect of maximizing these curves, so pushing them up, pushing up as early as possible. And because the horizontal difference between the inflow curve and the outflow curve is the travel time for each vehicle arriving in the network, this is the same effect as minimizing delay, so which is shown in red along the bottom. So if we take that objective function and we allow the solver to solve also for the signal plan, then we get an optimal signal plan for the network. So here we see the same example as before, but this time instead of using a predefined fixed signal plan, we've allowed the controller to optimize the signal plan, and this is the result. So perhaps not so clear, but you can see a lot more platooning happening. And you see much better coordination along this main north-south avenue. And in particular, you can see perhaps down the bottom here, you can see how the policy has been chosen to to coordinate between the cross flows of the traffic so that the platoons arrive in between each other and are minimized in delay. So that's perhaps a bit clearer if we look at a heat map of delay. So here we're just looking at focusing on the lane arterial link that we saw earlier in the example. And on the left here is the delay map for the fixed controller that we saw at the beginning of the presentation. And on the right is the optimized version. The red represents the amount of delay. So we can see that with the optimized controller, we're getting much better coordination along that, getting green waves coordinated down that avenue, and we're getting less delay compared to fixed time control. Okay, so now we have this model. We set about running some experiments to show advantages of having non-homogeneous time steps. So we defined a series of networks of increasing complexity, and we applied some input demand profiles to these networks, solved them for signal plans. But in particular, we applied this particular profile to some of the inputs where we have a change in demand on the networks. We have a burst of traffic arriving at some time in the future, perhaps a rush hour or something like that, where the traffic flow is going to increase. There's going to be a prediction of this increase in traffic flow, and so we can see what effect this has on the controller. So to do this, we use receding horizon control. So we generate a plan, what we call a major frame. So we pick some time horizon over which we predict the traffic flow, and we choose a discretization, which we give to the solver, and we use it to solve a plan. And then we take just the beginning of that plan that it returns to us, and we execute that plan on the network. And while that plan's being executed, we generate a new prediction and a new frame, which we then solve. And again, we throw away most of the plan, just keep the first part of that and start to execute that on the network, and so on, in a receding horizon control. But the difference with non-homogeneous time steps, we can use the dilation that we talked about earlier in the presentation. So we can, for the same number of time steps, we can extend that major frame over a longer distance, so we can predict further into the future. And we can, therefore, for the same number of samples, we can start to maybe see some of the long done profile. So therefore, we would hope that this would result in better coordinated policies, where it's able to anticipate future changes in the network and coordinate the policies between the different intersections to optimize for that. So we did this. Well, and also we also solve a single homogeneous time plan for the whole network. So rather than using receding horizon control, we solve the entire planning horizon for all of the time steps, which is quite expensive. It took quite a while. We let the solver run as long as it needed to, but this serves as a reference for the best we could hope for if we had the computational ability to do that in real time. So we did this. We used homogeneous discretization, and we had several different non-homogeneous discretizations. And so here you're looking at the results from this on one of the, along the bottom, we have the number of time samples. So we're increasing the number of time samples used for the major frame along the x-axis, and we're plotting the increase in travel time as a percentage relative to this reference solution that we solved, where we had no receding horizon control and unlimited amount of time to solve the entire horizon. So you can see that as we give the planner a longer and longer horizon, you can see this future change in traffic demand, and it can anticipate for that, and so it can get closer to the optimal signal control plan. So we see this convergence onto the optimal reference, and you can see that as we have a longer, so for the blue non-homogeneous discretization, we can see much further into the future, and we can see that compared to the green or the red, it's converging much faster onto the optimal reference signal plan, for the same cost, approximately, the same number of binary variables. Also, we can look at the quality of the solution. So here, we're looking at some box plots of the distribution of delay in the network. So we're looking at the we have the upper quartile and the median for each of the networks, and we're looking at here just a couple of sample points. We're looking here at 90 samples and 120 samples, and on the right there you see the box plot for the full reference solution. So you can see that as we increase the number of samples, we converge on the reference solution as you'd expect. But that with the blue homogeneous, non-homogeneous discretization, where we can see further into the future, we converge much more quickly, and we also find fair plans. So the maximum and the upper quartile delays are close to the optimal. We're not starving anybody, so we have a measure of quality. We find a good quality as well. Okay, so that was the experiments that we ran and presented in the paper. So now I'll just go through some extensions that we've used with this model. So one is to use the model to evaluate more fixed time control. So this gives us a way to evaluate adaptive controllers such as SCATs so we can compare optimal controller with a fixed time controller to see just how much better we can do, and also gives us a way to perhaps generate optimized schedules for existing fixed controllers. So we can take surveys of traffic, we can run them through the model, and we can generate schedules that are optimized, globally optimized, and take them out and load them into our controllers and use them on existing infrastructure. I'll also show you a way to use the model to optimize with the light rail. This interacts with the traffic. How we can use that to nullify the impact of introducing light rail to a network. And also briefly, I'll show you how we can also control uncontrolled intersections, so that the model is able to optimize for intersections which don't have signal control by optimizing the signals of the surrounding neighborhood intersection. So we can use QTM to solve for a fixed time controller, and so here we've constrained the controller to only allow it to choose an initial offset for each phase and a duration for each phase. So while it can choose an individual offset and duration for each traffic light, it has to use that for the entire planning horizon, compared to QTM, where it can arbitrarily change this at any point during the plan. So here you're looking at some time distance plots again, overlaid with micro simulation, and on the left you see with a fixed time controller the results. So you can see that it's found a coordinated schedule along an arterial route here. So it's chosen the optimal offset at each along the link at each intersection to get this green band going, and it's chosen the width of the screen corridor, the duration of the phase has been chosen same at each intersection, and it's chosen an average length duration for that. So the volume of traffic is varying over time. If you look at the traffic flowing in along the bottom, you can see that the density of traffic is varying over time, but it's chosen a duration that's the average for that. So it's had to trade off between periods of high flow and low flow. Whereas if we compare that on the right with full QTM optimized control, we see the same sort of thing. So it's found coordinated policies. It's using that to get green waves going along an arterial link, but it's able to adapt this green band to the volume of traffic, so it can increase or decrease that to optimize that to the volume of traffic. We can also use this to optimize for light rail. So if we add light rail to a network where the intersections have to be shared between the light rail and the traffic, we can then add constraints to the model to allow for that. So we choose a schedule for the light rail, and we apply these constraints to the signal plan, so it has to respect that. So when a train arrives at an intersection, it has the priority, and traffic has to wait. And so here's an example of that. So we have some box cars traveling along on the light rail through the network, and you'll see when it passes through an intersection, the light changes to red, and the traffic has to wait for the train to pass. So we did this with both the fixed controller and the optimized controller, and we did it before headlight rail and after headlight rail. So here you're looking at a lot of those results. So you have along the x-axis, you have increasing traffic demand or increased volume of traffic flowing through the network versus the average delay in seconds for an individual vehicle traveling through the network. So you can see below a blue plot is using a fixed time control. Before we had light rail. So you can see that as the traffic volume increases, it does reasonably well until it reaches a certain level of congestion where it starts to rapidly increase and delay, where basically the fixed controller has reached the maximum green band and can no longer adapt to the traffic level of traffic in the network. And then when we add the light rail to the network with the fixed controller, we look at the dotted blue line. We can see this has a detrimental impact on delay because of the effect of the schedule of the light rail. We can't coordinate so well with the fixed schedule of the traffic lights, so we see this increase in delay quite steeply right from low levels of traffic volume. And then if we use the optimized QTM controller in green here, we can see that actually we can almost nullify the impact of introducing light rail. The delay is close to before we had light rail with a fixed controller. And also, as the traffic increases, we offset the onset of this congestion. So we're able to handle higher levels of traffic flow in the network before we reach this congested traffic flow phase. And so if we look at some heat maps again of that, on the left we have the optimized with the light rail, and on the right we have the fixed controller with the light rail. And this is for traffic volume of 3,400 vehicles per hour. And you can see where red represents delay, you can see the increased level of delay there, particularly around the central intersection where the two light rails cross each other. And if we increase the volume of traffic to 4,300 vehicles per hour, you can see that as I do that, there's very little change in delay for the optimized controller, but a huge increase in delay for the fixed controller. Same volume of traffic. And so finally, we can try to optimize uncontrolled intersections. So we can introduce constraints where one flow has to yield to another. So we could have unprotected turn where traffic's turning across oncoming traffic flows, or we could have crossing traffic flows like we see in this example here. So here the horizontal flow has to yield to the vertical flow in this middle intersection. And here we can see that the controller has used the surrounding intersections to optimize the arrival time of the platoons of traffic at the middle intersection where there's no traffic signal control, so they try not to interfere with each other and don't delay the traffic flowing through that uncontrolled intersection. So that's some interesting extensions. Oh yeah, in conclusion, we presented a novel model of traffic flow called the Q transmission model, which supports non-homogeneous time steps and allows us to globally optimize traffic flow by scaling to many intersections. Compared to homogeneous, we've shown that for the same cost, we can converge faster on the optimum solution, or more or less the same, if not better, quality in terms of delay. And I've shown you some extensions that we can use with this model to do some interesting things, such as mitigate light rail or control uncontrolled intersections. And for future work, as I mentioned earlier, we only need to sample the QTM where there are piecewise changes in the Q dynamics. So it would be interesting if we could solve exactly for this delta t, exactly for these points. So recently, actually, I've managed to do that by making delta t also a variable in the formulation, and then we can get the exact solution for delta t as well as for the Q variables themselves. The problem when you do that is that if you want to have an objective function based on time, then you end up with a bilinear term in the objective function. So that's a problem to overcome still to make that useful. But we're certainly able to solve exactly for QTM using that approach. We'd like to be able to do full closed loop control with model predictive control. So we want to be able to learn parameters from the network data, and then initialize the model from the state of the network and proceed in a fully closed loop mode. And it'd be interesting to compare QTM with some of the other competing milk formulations, such as QTM and LTM, and also to compare that with some existing controllers such as SCATs, and using real traffic data just to show how well the model performs with real data. And also to scale up, it will be interesting to see how big we can get. We're using a MILP. At the end of the day, there are limitations to scale up. It's complete. So we probably need to look at using some sort of decomposition to get really big scale-ups. So finally, the code is all available on GitHub. If you're interested in looking at QTM yourself, you're welcome to download the code there and see how to use that. And yeah, so thank you for watching this presentation. I'll take any questions if you have them.
Thanks, Iain. Any questions for Iain?
Thank you, Iain. This was very interesting. I have a couple of quick questions.
Sure.
So, in terms of the locations of sensors and the existence of any mid-block intersections, or if there was you mentioned FIFO, so if this was a multi-lane link segment instead of a single lane link segment, how do you foresee this affecting the model?
I'm not sure I quite followed the question. So if just repeat that for me. Sorry, I missed the beginning.
Sure. Yeah. So the model, the tracking and the forecasting of the Q with propagation. So I see you mentioned FIFO, that your model is based on first arrive, first leave models. So my question is, how do you think your model would fare if you have multi-link segments when the FIFO assumption is invalid, or if you have mid-block intersections, so you have driveways on the highway, or you have shopping centers where you don't have signalized intersections between the different segments?
Yeah, so we can have outflow and inflow from internal links as well. So we could capture the effects of traffic leaving somewhere along a link, so parking, coming in or out of a parking deck or something like that, or parking up on the side of the road. I guess the assumption is that we're not really interested in the dynamics along the length of the link, only at either end of it. So we don't really need to know exactly the density at every point along the link. Just need to know when traffic is arriving at the end of the link, and we just need to know the rate of outflow from the link. So when we have a queue formed at the end of the link, then the traffic can flow out at the maximum rate into the downstream that the downstream links will allow. And when we don't have a queue, traffic can flow out at the same rate at which it's arriving into the network. So for sure that assumption will fall down. if we have a long link and we have a lot of traffic in the link, we will get some congestion. We'll if you're familiar with the fundamental dynamic of traffic, we'll start to go down the other side of that parabola into the congestion phase. So while that's really useful on something like a freeway, but I think our assumption is that for small, dense urban networks, it's the queue behind the intersection that's dominating. Once the queue is formed, it doesn't really matter. All the traffic has to enter into that queue before it can leave the link. So that dominates the dynamics of the link. That's the assumption that we make. Is that answering your question?
Yes, absolutely. Thank you. So my second quick question is, you mentioned the real-time computation ability. Do you have any statistics about how fast are the computations being done? So what is the possibility of actually implementing this in real time in the field?
Yeah, so for the networks that we presented in the paper, the largest network that we presented was this one with 9 intersections and multiple bidirectional flows and diagonal flows. So with this network, using a cluster, we were able to solve in real time up until like if we look at the results plots. So for the number of samples where it starts to converge for the non-homogeneous for the blue, so around about 90. So around about this point, we're able to solve in real time. If we were planning, if we choose a major frame time of about 100 seconds, if we give the planner 100 seconds to plan, then it can solve in real time. Not for the non-homogeneous. So for 120 samples, it takes longer than real time. So I guess that was about the limits that we could achieve with the model as we formulated it using Gurobi, commercial solver on a cluster with I think we had 12 nodes per CPU on that cluster. So I guess that's about the limits that we can achieve, and I guess beyond that, we'd probably have to start looking at some sort of decomposition.
Thank you.
Any other questions? So Iain, I also have, I think, follow-up questions to the ones that Ali presented here. I was also wondering about, I was concerned about also some of the limitations of the model that you develop in terms of some things that came to mind would be the intensive data requirements for the model to work, to be implemented, whether it is capable of accounting for the geometric complexities of some intersections, the existence of turning lanes, dedicated turning lanes, or complicated phasing plans if needed, things of that sort. So can you comment on that? Because I know using the CTM, and as Ali mentioned, I think there's a potential for a violation of first in, first out when you have multiple lanes because of the way that cells operate and the traffic moving from one cell to another. So it doesn't allow for any kind of lane changing or things like that.
Yeah, so we don't model lanes necessarily, but you could, for example, if you had a turning bay, for example, you could split the link at the start of that turning bay and have one link for the turning bay, one short link up to the intersection for the turning bay, and one continuing on to the straight ahead traffic, for example. There's nothing to stop you doing that. You can have arbitrary phases, so you could have dedicated phases for the turning bay, a dedicated green arrow, that sort of thing. And we've added extensions for yielding, so you could have unprotected turns, so that you could add that link for the turning bay, and it would have to yield to the oncoming traffic, for example. And we've shown that the model's able to do that as well. So does
the model allow also for some flexibility in the phasing plan, and you think about the way that actuated signals operate, in which some phases can be skipped, is this the same, or it has to be following a specific phasing plan?
It has, yeah. So that's an interesting suggestion, one I'd like to look into as well. But so currently, no, we don't support skipping phases, so it can't arbitrarily adjust turn off a phase or skip it, but it can only control the duration. So you could simulate that by having perhaps a really a phase that can become very close to zero. And get that behavior that way. So you'd expect the controller, if there's no traffic waiting, it wouldn't choose a long phase time, it would just choose some, a couple of seconds or something like that. So it should be possible to sort of simulate that effect. And also we can simulate the effects of lost time, startup lost time and yellow, or just a turning penalty associated with all red around the intersection. So we can have these sort of small phase times, so we can have an arbitrary complex phase plan for an intersection. There's no problem with that. It supports it. Unlike some other models based on CTM that doesn't develop that level, they can only support one binary variable for east-west or north-south, something really simple like that.
Okay. So my last question here is, I'm not sure if maybe I missed that part. I was paying attention. When you're doing the optimization, you are doing this optimization in real time. Are you doing it in a proactive way, for example, in which you kind of anticipate what the traffic demand is going to be on the link? And if there is some kind of prediction, how would you do that? How do you predict the traffic? Do you include, for example, because this is a network in which the travel demand on a particular approach could be affected by the signal timing of the adjacent intersections, because of the throughput and all this adjustment. So again, it gets complicated when you try to project what the travel demand is going to be in the next 5 or 10 minutes, or there is no prediction involved. I'm not sure.
Yeah, so we assume, in this paper, we assume that we have that knowledge. We have some way of predicting the evolution of the traffic flow in the network over time. That's not something that we focus on, but it's something I'd like to work on more in the future with this model. And again, you need to sense the state of the network as well, right? You need to measure where the cars are in the network with computer vision, with roadside sensing, with loop counters and that sort of thing. So, we assume for this experiment, we assumed it had this perfect knowledge of the network. Obviously, in reality, you would be somewhere. You'd have some partial observation of the network state, and that's something that'd be interesting to look into in the future with this model. But I think the main thing is that the cost of this model is so cheap. I don't know if you've used a North formulation of CTM, but there's just no way you can scale it up to more than a couple of intersections. Very infeasible, especially with a good time discretization cost. It's not even really worth comparing with QTM, because you can't really do anything more than a couple of simple intersections before it takes really time to run. So, I hope this model allows us to explore some of those things that you were mentioning in the future.
Yeah. Well, it'll be really interesting also to see. I saw in your last few slides that you're in the future you're also planning on looking into comparing this model with adaptive signal control to see, because you compare it to the fixed time, obviously, there's going to be a huge difference. But if you compare this to adaptive, I wonder how that's going to fare in the comparison.
Yeah. Yes, of course, there's problems there with getting micro simulations and getting licensing for things like SCATs. That's sort of holding me back from doing that at the moment.
Right. Sure.
It's something I'd like to do.
Okay. Any other questions?